A custom application powered by the scalable end-to-end logistical simulation, SEALS, can be developed using Mimic's modular design approach. As an example, Mimic has developed the port analysis simulation for the Virginia Port Authority. The tool can be used to perform throughput, bottleneck, and cost analysis on VPA's current infrastructure and resources. It can also be used to perform what-if analysis on increasing or decreasing infrastructure and resources. The tool can also be used to do proactive and reactive security analysis by injecting inspection stations into cargo operations and creating and injecting disruptions into normal operations. Business rules are captured as process flows to the level of detail required by each customer. The process flows capture operations within the infrastructure at each port and terminal, and the flow of cargo and transports between them using different types of resources. This high-level representation of NIT process flows for import cargo operations demonstrates loaded ships arriving at the terminal, moving to the berth, and the resources required to do so. A more detailed view of berths shows specific interactions. The tool provides the user with the ability to modify processes independent of the simulation and provided as input to the simulation at runtime. This feature makes the tool more responsive to experimental or operational changes by allowing the user to make rapid changes to the process flows to reflect current operational and analytical requirements. Port analysis simulation solutions are a collection of scenarios, profiles, and simulation runs. The tool is customized to gather data from external data sources to establish a baseline of current operations. Infrastructure data is populated from GIS data sources, and resource data comes from asset databases provided by VPA. This scenario analyzes the Port of Hampton Roads, a seaport, and the Virginia Inland Port, an inland cargo transfer facility. The scenario designer uses a hierarchical top-down approach with increasing levels of detail. This scenario uses two of the four Hampton Roads terminals, NIT and APMT. Areas and resources shared across the terminals are modeled at the port level. At NIT, there are 18 berths with a total length of 14,000 feet and approximately 10 million square feet of staging space. The defining characteristics of individual areas, such as length and depth of berths, can be viewed and modified. The same level of fidelity is available for all types of areas, such as staging and rail spurs. The effects of adding additional infrastructure can be analyzed by adding additional areas. GIS information for the area can be defined by creating a polygon. The capacities are automatically calculated based on the dimensions of the polygon. The characteristics of available resources can also be examined and modified. An operational cost can also be defined for each resource. The effects of acquiring or dispersing resources can be analyzed by adding or removing resources. The time it takes to complete each activity within the different areas defined in the business rules is modeled by process times. This time represents how long it takes to unload a container from a container ship using a container crane. The times are represented as mathematical distributions, and they can be modified. The time it takes to travel between areas, terminals, and ports is modeled using routes. Each route has an associated time, which is calculated from the distance and the speed. Routes are automatically created and calculated for every possible connection defined in the business rules using GIS data. All costs can be viewed and modified in a central location. Custom interfaces can be developed to present relevant information such as cost for financial personnel. The quantities and destinations of cargo and transports that flow through the infrastructure for a particular analysis are defined in profiles. Profiles can be created to model current loads or model projections of future demands. Profiles can also be created for cargo data that exists in customer repositories such as cargo manifests. Cargo can be containers, breakbulk, pallets, people, or any other type defined in the business rules, and the characteristics of each type can be modified. Transport types, whether real or conceptual, can be defined like cargo types. A profile is made up of a collection of arrival events. An arrival event defines when a group of transports of a specific type arrive. A transport can start empty or loaded with cargo loads. A cargo load is a collection of cargo that follows the same route. Each segment of the route is defined as a destination and the method of which the cargo will leave the destination. Required clearance time can also be specified for each segment. In these example profiles, there are 20,000 import containers, 24,000 export containers, and approximately 24,000 transports defined. The scenario and cargo profile can then be simulated using the SEAL simulation core using the defined business rules. All this data is provided as input to the simulation at runtime. SEALs is a scalable, high-performance, discrete event simulation capable of modeling each piece of cargo individually and capturing all types of data about cargo, transports, resource, and infrastructure utilization. In approximately 20 seconds, a total of approximately 1.6 million events are executed by the simulation, simulating the movement of 44,000 containers through the entire logistical network across 11 real-world days. The output follows the same port, terminal, and area hierarchical structure as the scenario designer. Data can be collected for all relevant metrics at any level. At the terminal level, the same data is broken down per terminal. Utilization statistics for all areas is available for both cargo and transports. The maximum value defined by the scenario can also be shown to demonstrate how much of the total available is being utilized. Utilization of areas can be viewed in greater detail. In berth footprint, the time and placement of individual ships on berth can be analyzed. The utilization and cost to operate resources can also be analyzed. Based on the quantity of cargo defined, this graph shows that of the 16 container cranes available, the max ever used is 8. The utilization data and cost defined in the scenario is used to calculate the daily cost to operate each resource. The total cost to operate all resources at a terminal is also available. Proposed additions to a port can be modeled by creating a completely new terminal within a port. VPA has proposed building a new terminal at Craney Island to accommodate increased cargo flow through the Hampton Roads port. A new terminal can be created by placing it on an appropriate area on the map. Proposed areas within the terminal, such as berths, staging, and gates, can be added by placing them on the map. Routes between the newly created areas are automatically calculated based on the distance between the areas. After the terminal has been created, cargo can be redirected from other terminals, or additional cargo can be created and the results analyzed. To summarize, the tool enables high-fidelity modeling of a logistical network with customer-defined cargo material, business rules, and transportation assets. It also enables testing and analysis of the logistical network, providing detailed data about cargo throughput, infrastructure, and resource utilization, cost, and any other measurable metric.